Okay, Assalamualaikum warahmatullahi wabarakatuh. Alright, so last video we covered the closed loop control of DC drive. So this is the main objective of taking this EPU 640 because mainly it is all about controlling the DC motor as well as the induction motor. Okay, how to control the motor electrical machines. Right. So before we go to the closed loop control or DC drive, we have covered looking at the main transfer function of the control itself, and then we also look into the transfer function for the converter. Right. So we have to go part by part until we give a complete closed loop control of the DC drive, whereby how we can control the speed of the motor by considering uh, the torque, the load torque, the currents, the armature voltage control. Okay, so we need to consider all of this before we go for the closed loop control of DC drive. So just to get refresh before we continue with these contents of the closed loop control, we just go back and look into the closed loop control. Improve accuracy, fast dynamic response, and then we talk about the block diagram of closed loop converters fed separately cited DC drive. So this is where we have the output, or we sense the speed in terms of radian per second omega there, and then we compare with the reference voltage, right? So the area of that will adjust the speed controller, and then thereby whereby the speed controller will produce a voltage to the converter, and therefore it will control the converter in terms of firing angles. We have this duty ratio in terms, and that will actually control the armature voltage in terms of VA there. Okay, and we start with the open loop transfer function. We look at the separately excited motors, the transfer function of the separately excited motors, and we only focus on that separate excited motors. But then we can, after you understand what's going on the separately excited, then you can apply the same understanding to the series type of motors. Okay, so we have that, and then this is the equation, the normal equation, the steady state equation, and then we convert into the Laplace transform. We transform to the Laplace transform. Then we look into the current equation, the armature current equation, and then the motor speed in terms of omega, and then there is a mechanical time constant tau m. We're going to look at a lot of time constant in terms of tau. Okay? So I hope you have referred to the Rashid's book. Most of the derivation in my notes will refer to the Harun Rashid's book, right? So just follow that book, and inshallah, I will try to add some more information to the slides with regards to explaining what in the books. Okay, so we did discuss on this until we look at finally we stop at we continue with converter control models. Okay, so this is a DC-DC converter. Then we look into single phase converter and three-phase converter, and this is the transfer function of the converter. And then we look into the closed loop transfer function, whereby we look into in terms of the feedback there. Now we have the feedback, we have speed, and then we have K1, and then it transforms into VB, and then compared with the reference voltage, as I mentioned earlier. Okay, so I think we have discussed up to this point, whereby by having that block diagram or transfer function there, then we can consider or look into the what happens to the speed subject to the change in the load TL, okay, the torque here, as well as to the reference voltage VR. So we did that, and we have this transfer function whereby it relates between the output speed with the reference voltage, right? So this is transfer function. In doing that, you set the torque into 0. So if you can refer back to your notes here, you can see that now okay, in order for us to look into the relationship between the output speed and the reference voltage, so we need to consider the torque equals to 0 here, isn't it? So there is no summation here. We remove that, and this is the block diagram of the transfer function, and then you solve that to get omega s with respect to VR, and you get this equation here. Okay, the transfer function. Next, we look into the what happens with VR equals to 0. So we have the reference voltage now is 0. So this comes from the plus minus, so the summation of plus minus before, right? Since VR equals to 0, so you need to have to maintain that. That's why you have negative there. So if you solve this, then you get the omega s respect to the load torque. Okay, and you can see that. All right, so now, and then this is a change. Then we look into the example, some of the examples there. So we complete that. Now we're going to continue with the whole complete closed loop transfer function. Right, so just now we have look at the block diagram for closed loop control, whereby we only have omega s with respect to VR, the reference voltage, as well as the load torque. But in practice, if you read this, okay, in practice, the motor is not only required to operate at the desired speed, okay, but it has to meet the load torque, which depends on the armature current, right? So while the motor is operating at a particular speed, if a load is applied suddenly, the speed falls. Okay, the speed falls as you have for example, we have a step change. The load increase from TL1 to TL2, for example. Okay, I hope you can see that. Then you're going to see that the speed will drop, isn't it? So the speed falls, and the motor takes time to come up to the desired speed. So uh, uh, the controller here will work. The closed loop procedure will work until you have the error appear here, isn't it? So it can be quite slow. Right? So there is a need, right, for us to have the current control loop, whereby we also not only sense the omega s here, we also sense the current, because we know that the torque, okay, we can have torque equals to K flux I A, isn't it? The armature current. So once torques increase, IA also increases, isn't it? So if we can sense the armature current, and we have a inner control closed loop for the current, then the speed will actually um, the motor will we have less times. It will go quickly to the desired speed, even though it could drop a little bit, and then it will go faster to the desired speed. So we need that internal or inner current loop. So that's what we did here, right? In this block diagram here. So we introduce the additional IA there. Look at that. So we sense the current, and we have some filter here to remove the ripple. So we have the current, and then we compare with the reference currents here. Okay, so we have a reference current here, compare with that current, and we produce an error here. So that error will have some adjust the current controller here, and therefore we adjust the armature the armature voltage in terms of alpha, and then therefore your speed can be adjusted and back to the required speed, right? So not only we measure the speed omega here, right here, okay, this is for the speed, look at that, omega m, but we also measure or monitor the current, okay, here, right? So this is very much the idea. And then not only that, we have to understand the voltage through here, right? The voltage only can be varied up to V rated, okay, the rated voltage of your rectifier here. So therefore, if you want to increase further the speed, right, you have to maintain the voltage here at about the rated voltage, and in order for us to increase the speed, we need to have this field weakening control. Yeah, so we have to reduce the IF. Remember, we also have torque equals to K flux IA. Then we can also have K, another K here, K IF IA, isn't it? Right? So you can also reduce IF in order for us to increase the speed here. There is a method. So that's why you have this complete. In this block diagram, you have current control loop as well as the field weakening loop. Okay, so we can read this. A speed feedback with inner current loop provides faster response to any disturbances in speed command, load torque, and supply voltage. The current loop is used to cope with a sudden torque demand under transient conditions. The speed control above the base speed is obtained by the field weakening. So once you reach the VA equals to rated voltage, at this point the speed is known as base speed. Okay, this is known as base speed. Okay, and here it states that the speed control above the base speed is obtained by the field weakening while the armature terminal voltage is maintained. So once we reach the voltage here reach the rated voltage, it will maintain at that particular rated voltage, and again, in order for us to increase the speed, then we need to apply the field weakening current loop. Right, so let's look at the next slide. The output of the speed controller EC. So let's have a look at some explanation on the block diagram here. The output of the speed controller EC, so this is the output of the speed controller here, is applied to the current limiter. So we have a current limiter there. We set the current reference IA ref, so that will actually set the reference current. So we have the speed as well as the required speed, reference speed, and we also have this by having that information and speed controller as well as the current limiter, you can actually create another reference current to the current control loop here. Right. So the armature current IA is sensed. So IA is sensed here by a current sensor, filtered normally by an active filter to remove ripple, and compared with the current reference IA ref in that particular loop here. Okay, the error current is processed through a current controller whose output VC adjusts the firing angle of the converter and brings the motor speed to the desired value. So that error, so error will come from there actually. So there's a current, the error of the current. So that current, error of the current will drive the current controller here, and then it will adjust the VC. I hope you can see that. So there is a VC there. So that VC will actually translate into the alpha, the firing angle, then will trigger the full wave, full bridge rectifier here, full control rectifier, and therefore will change the current as well as the speed. Right, so the speed omega will be changed if you have an error here. Okay, so that's it. So in terms of closed loop control, I believe you only need to understand the process. You also need to memorize all the block diagram in order for you to answer the question. So the final or the test later on. I hope there is no calculation. Okay, right. So the motor is ready to correct the speed error and finally settles at new IRF. So the reference current also can be changed, okay, which makes the motor torque equal to the load torque, resulting in a speed error close to 0. So let's talk about the speed error. So we have a speed error here, equal to the 0. For any large positive speed error, the current limiter, so we have the current limiter here, limits the reference current to a maximum value IA max. So we have a, so we protect actually the controller here by having that current limiter. The speed error is then corrected at the maximum permissible armature current and max until the speed error becomes small and the current limiter comes out of saturation with IA equals to less than IA max. So the speed error is then corrected and the maximum, so that refer to that particular speed current control loop. Okay, then the speed control, now we talk about the field weakening. The speed control from 0 to base speed is normally done at the maximum field. Look at that, done at the maximum field by armature voltage control, and control above the base speed should be done by field weakening at the armature rated armature voltage. So that talks about the field weakening here. So in the field current loop, the back EMF EG, which is equals to VA minus IA, is compared with the reference voltage EG. So where is the EG? Somewhere here, isn't it? So that actually explain the field weakening loop here. So we have EG reference, so that is EG reference. Then we have the voltage measured, which is generally between 0.5 and 0. For speed below the base speed, the field error EF is large and the field controller saturates, thereby applying the maximum field voltage and current. So we go back to the armature voltage speed control to do that. So when the speed is close to the speed, VA is almost near to the rated value and the field controller comes out of saturation. For a speed command above the base speed, the speed error causes a higher value of VA. So that talks about this VA. Where is it? So we have VA here. So there is a VA there. Right. So the motor accelerates, the back EMF EG increases, and the field error decreases. So the motor accelerates, and then the back EMF. So the back EMF is somewhere here. EG increases, and the field error EF becomes 0, decreases. So EF actually somewhere here. So this is your EF, right? The field current error EF. The field current then decreases and the motor speed continues to increase until the motor speed reaches the desired speed. So that is a talk about the field weakening loop. And next, there's a speed control above the base speed is obtained by the field weakening while the armature terminal voltage is maintained near the rated value. In the field weakening mode, the drive responds very slowly due to the large field time current. A full converter is normally used in the field because it has the ability to reverse the voltage, thereby reducing the field current much faster than a semiconductor. Okay, so that's talk about the complete current, the closed loop control of a DC drive, whereby we have a current control, inner current control loop, as well as the field weakening loop there. Okay, right. So now we come back to the design of the current controller. So forget about that field weakening uh, loop. We just focus on the design of current controller here. So this is taken from previously we have this motor drive with current control loop. Okay, so this is actually represented by, here we have the current controller, here we have the converter transfer function here, right? So this is converter transfer function, converter transfer function, right? In this is known as the motor. Then we have this as a speed controller here, right? So that's complete a closed loop drive. Okay. Right, so PI controllers, let's consider PI control. So the transfer function for the current controller, so this is your current controller here. So this is the current control. Okay, the first one here. So that is the PI controller. We put in that particular GC. And then we have GS, which is the speed controller. Again, we apply the PI control here. So we have KS 1 plus S tau S divided by S tau C. Then this should be S. Mistake here. Sorry, so KS 1 plus S tau S divided by S tau C. So that's a speed controller, a PI control transfer function. And finally, you have a transfer function, which is the speed feedback, G omega WS. It's that one. Okay, so that is represented by that KW over 1 plus S tau W. Right, so this is the on the transfer function, not the PI control. Okay, right. So just to that, so you can see this. Okay, so you can see that. Right, so this is some revision. So if you have this transfer function, the block diagram, this is a plant transfer function, and this is a feedback transfer function. C is the output, R is the input, and we have the summation for the feedback here. And we can simplify the block diagram by using this transfer function of CS over RS, whereby it is equals to G, the numerator, right? Divide by 1 plus GS HS, the denominator. Okay, so the G multiplied by H is known as the loop gain. If you have that, and what we did is actually we remove this feedback, and then therefore you have a loop feedback. So this is loop gain transfer function. So it is a merely GS multiplied by HS. Okay, and then therefore the loop gain function of the motor drive equals to GS multiplied. So we have this as a GS, the denominator here. Okay, so that is GS, and this is to be your HS. Okay, so and therefore we have GS multiplied by HS. You just simply multiply these two and you get the equation here. So if you refer to the Rashid book, there is a bit of a mistake. I believe there's a mistake there. In, in, Instead of they use a tau here, they put as a TC. Okay, so that must be confusion, because you can see that it's a talk as well, isn't it? So that is, the symbol is actually tau C, tau M. This is time constant. Time constant. So check back your books, okay, the soft copy of the Rashids, and then you can make corrections there. All right. Okay. Next. So again, the loop gain function of the motor drive, just to repeat the same equation just now. That. So now we're going to look into how to reduce the system from 4. This is fourth order. Right, fourth order, because we have 1, 2, 3, 4 poles, isn't it? 1, 2, 3, 4 poles. So this is order of 4. So we can, to simplify the analysis, simplify the design of the control, we're going to reduce that fourth order to second order only. Right? So how to do that? We're going to assume that it is the 1 plus S tau M, the mechanical time constant here, this is very, very large compared to 1, and therefore you can estimate or approximate. So 1 plus S tau M is also equals to S tau M. Okay, and we have this condition, top 1, the torque for the motor here. Then we have top 2, and then we have top R, which is the converter. Come from that converter, and T2 equals to TC. So we have this. I believe this is a cancelling method, pole cancelling method technique in the closed loop transfer function. Okay, so again, this is loop gain GS multiplied HS, and when we did this assumption whereby S tau M is equals to S tau M, then you can replace that, remember, so you can replace that with SM here, and then TC equals to T2, so you can replace this with, if you like, no, what I did is, okay, so you're going to replace that T2 with tau C, so this is gone, isn't it? And therefore, if you look at that, you can actually wait, there is, so the same denominator and numerator, so you can cancel that, and then you can cancel this, isn't it? And finally, what left is this GSHS equals to K divided by 1 plus S tau 1 plus 1 plus S tau R. Okay, so that is the simplification. So we try to simplify the equation by considering these statements here, right? Then therefore you have GSHS equals to K divided by 1 plus S tau 1 plus 1 plus S tau R, and then you can rearrange that. So again, this is slightly different to what Rashid's done in the book. So there's page 744. Please refer back to page 74 and make corrections. Right? So K here equals to that, and you multiply that. That's why you have this K equals to that. All right. Next, the characteristic equation. I hope you still can remember while doing your control subject last few semesters. Okay, so we need to have this characteristic equation, because this characteristic equation actually determine whether your system is stable or not, isn't it? So the characteristic equation equals 1 plus g SHS, the transfer function just now. We have the basic closed loop diagram. Okay, so we have 1 plus here. So that you set to 0. Right? So that will give the characteristic of the transfer function that we have. Okay, so that is known as a characteristic equation, whereby you set 1 plus g SHS equals to 0. While doing that, therefore, you found out that your omega n here, I think you still remember, this is your equation again, general equation, s squared plus 2 zeta omega n, s plus omega n equals to 0. Zeta or lambda, I'm not sure. Okay, probably zeta, yes, 2 zeta omega n plus omega n equals to 0. So when you do that, then you can find actually the omega n, the natural frequency, 1 plus k divided by tau 1 tau 3. And then we also have this damping ratio. So damping ratio will determine the damp, how damp is your system is. So we have this 2 zeta omega n there. And if you complete, or if you rearrange the equation so that match the characteristic equation here, then you can find out that the natural frequency is equals to omega n equals to square root 1 plus k divided by s tau, tau 1 tau r, and the damping ratio equals to that tau 1 plus tau r divided by tau 1 tau r divided by 2 omega n. So by setting the damping ratio, if you set the damping ratio to 0.707 for critically damped, and this is the common value for the damping ratios, so that you can find out that your the transients is good, right? There's no oscillation, high oscillation, and under damp. Okay, so assuming k equals to 1 and torque 1 greater than torque 2, and this is actually based on some reference. So you can use that, and finally you find out that the controller can be expressed by this equation here. Kc equals to 1 over 2 tau 1 tau c divided by tau r multiplied by 1 divided by km kr hc dm. Okay, so that is very much on the closed loop transfer function, right? Don't worry. So I hope you just understand how you're going to plan, how you're going to do the design of control. Actually, this is only design of current control. If you refer to the books, I hope you go and look into the books, Russian books. So we also have another design, which is on we have this closed loop current control, and we also have the design of current control. Just now we have the design of current control. Wait, next is we have this. Where is it? Yes, design of speed controller. So just now we have a design of current controller. Now we also can have this design of speed controller. Okay, so I'll just leave it for you to read the section design of speed controller. Okay, you need, of course, you need to go back and open up your controls book, look at the fundamental, how to do the how to simplify the block diagram. If you have a cascaded block diagram, you can move the nodes here to the front or to the end. You can do that. sorry, block diagram. Okay, do that, and finally, I think that's it for the closed loop transfer function, closed loop control of the DC motor. So next, we're going to focus on how we're going to look into the induction machines. So at the next class we'll discuss on the DC drive, the drive for the AC motor. Okay, so of course it will be different from the DC motor drive. Okay, so with that, thank you very much. So we're going to see you again on the next video. Assalamualaikum warahmatullahi wabarakatuh. So don't forget to do all these examples here, exercise here, okay? And again, you have the current controller as well as the speed controller that you need to consider. Okay, Assalamualaikum warahmatullahi